Hi, good evening. How are you? Good. So if the meeting by any chance stops after 1 hour, I have given a link and I've pinned that in the chat box. Just copy that link and you can join if the meeting stops. Okay. Okay. Start. So this is the week 11 problem solving session on advanced atmospheric physics. So I think on 10th, that is this Friday, the same time, at 6 to 8 p.m., there will be another problem solving session. So there, what I am planning is that I will complete the week 12 part, whatever contents are there. So on 10th, 6 to 8, there is another problem solving session where I'm planning to cover the week 12 one, and the next week, the problem solving session which is there, which is usual Tuesday. So there, what I will do is that I will check out some problems, say some 15 to 20 numerical problems based on the atmospheric physics what we have studied. Because most of the numericals are from that, so we will solve those numericals. So it will be good for your exam purpose uh, if you are planning to give or register for the examination. So it will be good for you. Okay, so that is the plan. So today, uh, again, so I will start with the assignment 10 problems, few discussions, and once it is done, we will just start with the week 11 contents which are there. And the next session will be, I think, on Friday, 6 to 8 p.m. Uh, there, we will discuss the week 12 content and we'll finish the contents at least. And the next week, we will be doing some numerical problems uh, that will be helpful for solving questions in the exam. Okay. And I have also pinned a link, meeting link. Those were come recently. So if this meeting link stops after 1 hour, just go to that particular. uh, code which I have given. So in the Google Meet. Okay. So that is there in the chat box. Just follow it. Okay. So let us start with the assignment 10 questions. Okay. So let me just fill it. So this is the week 10 assignment. Uh, the first question is that the time it takes for the solar equator to execute one more full rotation than the poles in the same time is about. So what the question is based on is that the rotation of the sun. And we know that sun's rotation is not a rigid body rotation. Okay. So equator moves faster, rotates faster, and than as compared to that of the higher latitudes or poles. Okay. So in general, uh, what we generally know, and we have discussed it also in the last session, that s- sun's equator, sun's equator rotates roughly around, it takes about 25 days to rotate. Uh, that is one point over the sun. If it is rotating, one full rotation, it will take about 25 days. Whereas sun's polar region, its rotation period is about 35 days. So now, so remember this concept comes from that sun's rotation is not rigid body. Okay. Some portions rotates in a different period, other portions rotates in another different period. Okay, so it's not a rigid body rotation. So this is the concept, and we have to remember this, that 25 days for the equator and 35 days for the what you call as the polar region. Okay, so now let us count out. So this is suppose the equator and this is the poles. Okay, so the first rotation which the equator has made, sun's equator has made, that will be how much? It will be 25 days. Okay, but what about poles? 35 days. Second rotation, it will be covered in 50 days, whereas the second rotation for the polar region of the sun, it will be about 70 days, 35 into 2. Third rotation, this is about 75 days, and this will be 105 days. What about the fourth? This is 100 days. And what about this? This is 105 plus 35. Let us not write it right now. So the thing which is being asked is that equator gives one more rotation compared to the poles. So you can see that equator has given four rotation, has already taken four rotations in 100 days, whereas poles in 105 days it will complete third rotation. So it has already completed an extra rotation. Okay, within 105 days. So if the polar rotation period is, say, suppose, let us say that the time period is 105 days. Okay. So in the 105 days, poles will rotate three times. So 105 days, poles rotate three times, whereas equator rotates four times. So one extra rotation, you can easily find out that in the equator has already given one extra rotation compared to the pole. In how many days? Within 105 days. So this should be the correct answer. Okay, understood the question. So the question was that the time it takes for the solar equator to execute one more full rotation than the pole in the same time. So what is that time? The time is 105 days. Because in 105 days, poles rotates three times, whereas equator rotates 4 times. So this should be the right correct option. Okay. Next is the second question, that is, yes, bolo. Mhm, 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 mhm. हाँ, ओह अच्छा अच्छा, ओके, समझ में आया ना कैसे हो रहा है ये? हाँ हाँ, ये क्वेश्चन थोड़ा सा मतलब, एग्जैक्टली एग्जैक्टली। हम्म, एकदम ठीक। ओके, द सेकंड क्वेश्चन इज that air glow in green color, that is 557.7 nanometer. We have seen this of visible spectrum is caused by, this is just a book's definition. So electronic transition from atomic oxygen. So it is already there in the uh, whatever your lecture notes or the videos, you can easily find out. Next is intensity or locality of aurora least depends on. So it least depends on the atmospheric circulations. Other things are very important, particularly the shape of the magnetic lines, then energetic particle precipitation, and atmospheric compositions, of course. Okay, so just a one-liner I wanted to just write here for the third one. Okay, second one is electronic transition. This is known actually. So this is not transition of, okay, atomic oxygen. Oxygen is spectral jump, which we have. Third, third one, that yes. So least depends on. So the formation of that aurora, the location and sorry, not the formation, the location and the intensity. Location and let's say here, intensity of aurora least depends on. So it will just depend on atmospheric circulation. Atmospheric circulation has very little role. Okay. So what it depends on, all the other three options which are there, that is the magnetic field. Of course, because it is nothing but the charged particle which is being trapped by the geomagnetic field, and then those charged particles which comes near the poles and hits the molecular nitrogen or oxygen molecules or atom, and that results into a jump of the electrons, and when it falls, it gives you the photon of the color which we see for the aurora. So I will just write a couple of lines here that the process happens something like this. Charged particles, okay, charged particles from the sun, that is through the solar wind, it reaches the earth, and most of which are deflected by the magnetic field of the earth, the magnetic field lines which we have drawn in the last class. Not drawn, but I've shown you magnetic fields and towards the poles. And now at the poles, it interacts with the oxygen and nitrogen. And this gives you some photons. This interaction will give you some photons, which is seen as some visible color or visible spectrum, which falls in the visible spectrum. Okay. This is the a small or brief description of the location and the intensity of the aurora. So you can see. that the charge composition, that the charge particles, they are important. Magnetic field lines, they are important. And the interaction of the charged particles with the magnetic field, which is nothing but is given as one of the options, I guess. Yeah, the energetic particle precipitation. So these three are much more important compared to the atmospheric circulations. Next is, generally, the active regions of the sun are associated with. We all know that when active regions are generally associated with the sunspot numbers and the magnetic field, because sunspots are also related to the magnetic field, right? Because you know there are pairs of sunspots. So from one sunspot to another sunspot, the magnetic field lines starts and ends. So in that way, the strong magnetic field lines which forms a loop, that is the C option, and the A option is the sunspots. Actually, the number of sunspots activity, that these two things controls the active region of the sun. So A and C. Fine. The next is the structure of granule on the surface of photosphere is caused by. Okay, so generally we have seen that if you look at the sun's structure, this is the fifth one. If you look at the sun's structure, you will find out that the picture, it looks like some granular structure like this. Okay, so what this represents? This represents the convections which is happening. So there are three zones within the sun. Okay, in the interior of the sun has three zones. One is the core, of course, where the nuclear fusion process is taking place. One is the core. Second is the radiative zone, just above the core. The radiative zone is present, where ions are present, but materials, that is, ions are present, but they are not able to absorb the heat or the energy from the core. It is through radiation the heat or energy is being transferred. And third is the convection zone. Okay. So just after the radiation zone, particularly towards the uppermost layer of the sun, is the convection zone, which appears like a granular structure. That is, in some places there is a upward motion, and some places there is a sinking motion. So there is a rise and fall. So this is one granule, this is another granule, and like that way it tends to uh, appear over the sun. Okay, so this is the convective pattern of the plasma in the convection zone. So that is what is the granules on the surface represents. Next one, sixth question: which of the following planets does not have an internal magnetic field? This is also we have discussed in the last session. That is, Mars is the planet which does not have its own internal magnetic field. And this is which type of magnetism or which type of interaction? It is Venus type interaction. Venus also does not have a strong magnetic field or its own intrinsic magnetic field. Okay, so Mars is falling in the category of the Venus type. So that's why it does not have internal magnetic field. 17th, which of the following part of the sun is the hottest? This is easy. The core is the hottest region, of course. And the last thing, the ring current generation occurs. The ring current generation occurs due to the charge dependence of the gradient and the curvature drift in the magnetosphere. So we have discussed about the ring current. So I'm not going into the details. Okay. Uh, Fine. And also the solutions are already there. So I'm not discussing much. So these are the couple of discussions which is required for the assignment 10. Particularly the first question, it was important. So uh, yeah, that's all. Okay. So let's now jump to the week 11 context. Okay. So those who have came later, just one announcement that it may be possible that my Google Meet link might get exhausted after 1 hour maybe. So I have already pinned in the chat box one code, that is the meeting link. Just copy that right now so that if it stops, then you can rejoin with that particular link. Okay, fine. So let's start with the content. That is your first is the planetary magnetism. Couple of points. I will just list it down so it will be easier. So first of all, any conducting fluid, so just any conducting fluid in motion generates magnetic field, right? So Earth has its own magnetic field, right? So that's why one of the nature of interactions was the Earth-type magnetic field, which consists of its own atmosphere is present, also its intrinsic magnetic field is present. So how the intrinsic magnetic field, its own magnetic field, how is it present? It is present because the outer core layer in the earth, there are a couple of layers like the crust, the outermost, then the mantle, and then you have the outer core layer, and then you have the inner core layer. This is for the earth. Okay, so in the inner core is completely solidified, it's solid inner core. But just above the solid inner core, there is a outer fluid which consists of large number of plasma or charged particles or ions. Those, when the Earth rotates, they also rotate, and that creates a dipolar structure of the magnetic field. So that is what is written here. So if you have a planetary magnetism, most likely it is because of the conducting fluid in motion which generates the magnetic field. Okay. So for example, in case of the Earth, so the Earth fluid outer core is the conducting fluid. Okay, so on the conducting is conducting in nature. Okay, because these fluid outer core it consists of large number of charged particles or ions. Okay, so this is one of the things. So what this fluid consists of? It consists of several free electrons. So you can see free electrons are present. That means ions are also present. So free electrons which are released from the metal constituents, metals such as iron and nickel. Remember, our core, that is Earth's core, generally consists of these two metals, iron and nickel. Okay, so this core, in the inner core of the Earth, it is generally in the solidified form. But as you go towards the outer core, where it is mostly a fluid type of characteristics, which we can see, there you will find that these metals generally ionizes and results into large number of free electrons, which rotates along with the rotation of the Earth, causing the dipolar structure of the magnetic field. Okay. So now question is that how then these electrons or this ionization takes place? This ionization takes place due to friction or the heat which is present there. Okay, friction and okay. So this is the second point. What else? Okay. Now magnetic field. Okay, magnetic field is present or will be present in any particular planet which has number one a large fluid core which is there in case of Earth, large fluid core. Those fluid core will consist of rich in metals, which will ultimately result into ions and electrons. And the third is high rotation rate. Okay? So these are the couple of points which are important for the formation of its intrinsic planetary magnetism or its intrinsic magnetic field. Okay, so a planet having, I would say, heavy intrinsic B field or magnetic field if and only if these three conditions satisfy. Okay, so one important point that Earth is the only planet with strong magnetic. Okay, but let us see some examples like Mars and Moon have no magnetic field. This we have already discussed in the assignment. In the last session also, we have seen this. They do not have any magnetic field. B field is the magnetic field. Okay. So generally in physics, B is represented as the magnetic flux actually. So that's why it is used. Okay. So why Mars does not have its intrinsic magnetic field? Because Mars has a solid core. Our Earth also has one of the layers of the core as the solid core, but due to the outer core being in the fluid as a fluid, exists as a fluid, that's why we get a very strong magnetic field. And why Moon? Because the Moon does not have any core. The Moon does not have any core, but Mars has solid core. Uh, the both the conditions does not satisfy to have a intrinsic magnetic field. Okay, what about another planet? Let's say Venus. What happens to the Venus? It has molten layer. Okay, it has molten layer, which is favorable for having the intrinsic magnetic field. But because of extremely slow rotation rate, the Venus, you don't get to see the strong magnetic field there. Okay. And one last case example is Mercury and Jupiter. Both have a large magnetic field. It has rotation, and being the first planet close to the sun, you can see that the cores are there, which is having fluidic nature. Okay, and it has rotation period of about 59 days, but the magnetic field is small. It's not too high. Okay, so this is the thing. But in case of Jupiter, this has a large magnetic field because it has liquid metallic core plus it rotates also quickly. All right. So these are a couple of examples of the planetary magnetism. Different planets we have seen. A couple of statements I have just written. Okay. So the basic fundamental is that the conducting fluid, which is metal rich, due to friction or due to heat release, it will dissociate into ions and electrons. Those free electrons, when it rotates with the rotation of the Earth or rotation of the any planet, this creates a dipolar structure of the magnetic field. This is the core fundamentals. So these 3 points are important for creation of an intrinsic magnetic field for a particular object, which is the planet here, planet or satellites, whatever. Okay. Now, different planets, different national satellites have their own behavior, and as a result of which we can group it that some will not have a magnetic field, some will have a very small magnetic field, some will have a very large magnetic field. Okay, so this completes the planetary magnetism part. Next, let's go to the. Huh, it does not have intrinsic, extrinsic. अपना मैग्नेटिक फील्ड नहीं है. हम्म. मुझे लगता है एक्सट्रिंसिक है, मतलब बाहरी इंटरेक्शन से अपना मैग्नेटिक फील्ड जनरेट करता है, एक्सट्रिंसिक होना चाहिए सैटर्न का। नेक्स्ट, let's go to now the solar wind, characteristics of solar wind. Okay, so here also we will have some points. So solar wind exerts magnetic and dynamic pressure. So there is a difference. Okay. There is a difference between magnetic pressure and dynamic pressure. So where these pressures are being exerted on some planets. So these pressures are exerted on some planet or comets. Okay. So this thing first. So what is the magnetic pressure? So there are two pressure which I have mentioned. One is the magnetic pressure. As you can see, that solar wind, it also has some magnetic field because charges are in motion, so some magnetic field will be there. And this magnetic pressure generally is mathematically written in terms of like b square upon 2 mu naught. This mu naught is the permeability in free space. Okay. The second one is the dynamic pressure. Dynamic pressure is due to its motion, the kinetic pressure you can say. Okay. It is so dynamic pressure, which is rho v square by 2. You can see that velocity is playing an important role. Okay. So this is the pressure due to the motion, the fluid motion. Okay. So solar winds generally carries large number of charged particles at a very high temperature. So it will be a fluid definitely. It's a plasma. Okay. And it is in motion. So pressure due to the fluid motion is what you call as the dynamic pressure. And I think in the Bernoulli's theorem also we generally talk about some dynamic pressure part. And magnetic pressure is your pressure which is exerted due to the magnetic field of the constituent. Okay. So these are the two things. And in case of sun, in case of the sun, this D can be written as Bs divided by Rq. So Bs, this is the typical pattern of how the magnetic field changes as the distance goes. So now what is Bs? It is the field, that is the magnetic field at the sun's equator. Okay, so this is how the magnetic field varies as the with the distance. Therefore, the magnetic pressure Pb for the sun, in case of the sun, will be how much? So if it is b square by 2 mu naught, then it will be nothing but bs square divided by 2 mu naught r to the power 6. Right? So Pb is varying as 1 upon r to the power 6. Okay. Whereas the dynamic pressure, Pd, the dynamic pressure, will be varying with 1 upon r square. Why 1 upon r square? Because you have your this the v square term is there, and in general it is seen. I cannot write the actual formulation here, but the dynamic pressure is seen to vary as 1 upon r square. Just like the energy density, as you go outside, it depends on the area, right? So 1 upon 4 pi r square. So this 1 upon r square part is coming here. Okay. So P dynamic is proportional to 1 upon r square. So now if you compare the magnetic pressure and the dynamic pressure of the sun's or the solar flares which is released from the sun, then what you will get? You will get that your PD at As the distance, as you go higher distance, PD is much, much greater than PB. Why? Because it is inversely proportional to the R to the power 6. This is inversely proportional to the square of the R. So as R increases, so what will happen? So this will be much, much lower as compared to this. So the dynamic pressure is much greater than that of the magnetic pressure. Okay. So at larger distances from the sun. Okay. So this is one of the things. Another thing, I was looking into it. It was not greatly mentioned. Let me see whether at that point I have it or not. What is that? Some beta plasma. Just a beta plasma. This is its definition is actually it's a beta parameter. Okay, beta is a parameter, so dimensionless ratio of thermal pressure divided by your magnetic pressure. This is the beta. For in case of plasma, because you can see that charged particles, microscopic particles are in motion, so there will be the thermal, that is the temperature based kind of a. So microscopic kinetic energy will lead to increase in the temperature. So the thermal pressure, this can be calculated using NKBT, that is ideal gas law, and the magnetic pressure we have discussed. So these two ratios gives you the beta parameter. And so if beta is much, much greater than 1, that means the pressure is greater than the magnetic pressure. So generally solar winds have a large beta factor. Okay, so beta plasma is larger in case of solar wind. So just a diversion from this, since I am talking about the pressure, I was just looking into it yesterday. So this just to remember is required. Okay, let's now go to a very interesting phenomena called the Parker spiral, discovered by Parker. This is Parker spiral. Okay, so what is the why spiral term is coming? We will come to it. We will see this. But before that, we need to know that the solar wind propagates outward from the sun, carrying a magnetic field. Now, why it carries magnetic field? Because one of the reasons I can say is that the solar winds are coming from the sun, and it has a plasma which consists of charged ions and electrons. When it is in motion, it will always be having some kind of a magnetic field, because when the current is generated, you have this Ampere's circuital law, which results into magnetism. That is what I think. This way, the magnetic field will be there. It will be propagated with the solar wave. Okay, so it is carrying the magnetic field from the sun. Now, why it produces a spiral is that, see, the solar wind. So this is suppose the sun. Okay, and the solar wind, suppose it is traveling here radially outward. Okay, solar wind is traveling radially outward, and there will be a magnetic field, of course. What happens is that sun also rotates, right? So as the sun rotates, and there is a radial component, so what will happen is that it slowly becomes like this. Okay, and it continues to be like this. So a spiral motion will be same, or a spiral structure will be same of the magnetic field. Motion is the wrong word. Spiral magnetic field. Initially, it will have a radial magnetic field as it goes radially outward, but this radial magnetic field will be uh, influenced by the solar rotation, and that results into this spiral magnetic field. Okay, and this is what you call as the Parker spiral. So let me write it. So produces a spiral structure, a spiral magnetic field, okay, spiral magnetic field, which is being carried out radially outward as the sun rotates. Okay, outward as the sun rotates. As the sun rotates, okay, as the sun rotates, it creates a spiral. So a lot of visualization is required that what is actually happening. Okay, and finally, one point is there. So charged particles such as the electrons, protons propagate along the spiral. Just like what happens in our case, that is near the Earth's surface or near the Earth's atmosphere. So what happens is that the charged particles from the solar wind comes and it gets trapped into the geomagnetic field lines, and then it tends to follow a helical path and it forms ring currents, which can result sometimes in the poles in aurora and all those things. Exactly similar kind of a pattern. Okay, so just another point, we were talking about the radial magnetic field. So this BR, the radial magnetic field, remember it is proportional to the distance from the sun, distance from the sun. It depends on the latitude at which it is happening, and it depends on the solar wind velocity. Interestingly, it does not depend on the sun's original magnetic field. It depends on these three things. Okay, just this is another thing. Many of the things is not very well known. These are based on some laboratory measurements or some pictures which has been uh, which is there with us. And then with the theoretical development we have come up to this point. Okay, many of the things are not explained, that why this is uh, not dependent on the magnetic field, why we are talking about the radiation zone. Then we have the surface of the sun where the temperature suddenly gets inverted. So why that happens, many of the things are unanswered right now. So it's a deep research scope is there. So okay, so this is another thing. Okay, let's go to the effects by the solar wind, or the solar wind effects. Okay, the solar wind effects of the solar wind is, remember, this is solar wind effects. The solar wind is coming near a particular planet. How it will affect with the planets, or it the planet's magnetism, or whatever related to that. Okay, so solar winds, it depends. The effect will depend on, of course, the magnetic field, and of course the atmospheric properties, like the compositions, what are the things present as per atmospheric properties of. When I'm writing object, remember this object means planet. Okay, yeah, planet or comets, or the natural satellites, whatever it is. Okay. Next is planet with magnetic field essentially have a dipolar structure. In case of Earth also, we generally say that there is a dipole structure of the Earth's magnetic field. Okay. So essentially have a dipolar structure. All right. So B of Earth, generally the magnetic field, radial magnetic field, is somewhere like this. 1 upon RT. The dipole structure, you get this kind of a formulation. Okay. Now, when this solar wind interacts with the magnetism or the planetary magnetism, then couple of magnetosphere is one of the layer which is being created. So there are two types of magnetosphere. One is induced magnetosphere. What is the induced magnetosphere? And the second is the intrinsic magnetosphere. We'll come one by one. Okay. So induced magnetosphere is that when you have solar wind interaction, interaction that creates that creates the magnetosphere. Okay, that creates the magnetosphere. Okay, and increasing is that when the object, again object, remember it is a planet, object creates its own magnetic field, own magnetic field, and when it interacts with the solar wind, that creates a magnetosphere. Okay, so these are the two different things. Okay, in case of induced magnetosphere, planet might not have, planet may not have its own magnetic B field. Okay, so okay. Now, a couple of more points are there. So, in case of induced, it will not write completely. Okay, so induced magnetosphere is magnetosphere. So, you have either a category where there is no magnetic field, or not or, and no atmosphere. So neither the atmosphere is present nor the magnetic field is present for a particular object, for example, moon or something else. Okay, this is one of the things. The second one is you can read it about the no field and no atmosphere from the lecture notes of the NPTEL. So you can uh, outline that what are the actual properties of those objects. And the second one is that there will be no field definitely, but atmosphere is present. Atmosphere is present. So in which case these are seen? These are seen in case of Venus or Mars. Field is not present, intrinsic magnetic field is not present, but atmosphere is present. Okay. Whereas on the other hand, in case of the no field, no atmosphere, it is the basic thing is the moon. Okay. So solar wind directly hits the earth and then outgassing processes and all those processes. There are many things. Just read all those things. It will be helpful. So one important point is that in case of induced magnetosphere, there is a region called ionopause. Okay. So what is an ionopause? Ionopause is that region or that I would say yeah, that height maybe, or that distance at which thermal pressure of ionosphere becomes equal to, it's an equilibrium point, dynamic pressure of the solar wind. Okay, so this is the ionopause. So let's calculate now the height of the ionopause. Okay, so what we generally use for the height of the ionopause is that we use the hydrostatic equation. So dpdr is, instead of z we are writing dr, radius of distance. Okay, is equal to minus rho times g. Okay, and remember this rho, this is the density of the ions of the plasma which are present. Okay, so now dpdr is equal to, rho can be written as what? Minus p by rt from the ideal gas law into g. Finally, we can further write dpdr as minus p, and this, what I do is that I write it like this, and this r can be now written as the Boltzmann constant times p. Okay, because k by n is the gas constant. So that is what the change I have made. So R is nothing but the Boltzmann constant divided by the mass. Okay, so this is one of the things. Next, what we will do is that we will take out the P on one side and other terms on the other side. Mg by kT, and this is dr. So we will take P naught as some point and P as some other point. So initial point and final point. So P naught is, let's say, at R naught. This is at R. Okay. So you can understand that dP by P integration will give you log P from P naught to P integration, and mg kt, they are all constants, and this will be R minus R naught. Perfect. So what next we can do is that this is simple exponential expression. You can understand P naught exponential minus mg by kt. Oh, there is negative sign. Okay, into r minus r naught. Now here, what we will write is that P is equal to P naught, similar expression, but we will write in a different way. So minus r minus r naught divided by h. So this h, again, as you remember, we have done a similar kind of a thing in when we were talking about the ionosphere. We were talking about scale height. So this is h is, again, this is the scale height. Okay, this is the scale height. This scale height is defined the same way, kt by mg. Okay, so p is equal to p naught e to the power minus r by r minus r naught divided by h. So r naught is the reference. You can keep it the surface where r naught is, let's say, 0. You can make it 0, and the p naught will be of the surface position. And as we go up, this is how the expression looks like. Okay, so ionopause. Another definition of ionopause. Let me write. This is much more related definition. That is the pressure due to solar wind equals the pressure of planetary atmosphere. This is much more relatable. You can understand this. Okay, because we are talking about the hydrostatic equation of the atmosphere. So this is the pressure of the planetary atmosphere, which will be equated with the dynamic pressure of the solar wind. So P of the solar wind, which is the dynamic pressure, will be P of the planetary atmosphere. Now, what is the dynamic pressure of the solar wind? Let us write. This is nothing but ESW, which is half the same definition, rho of the SW and V SW square. So earlier when we have written this rho, this was the density of the atmosphere. Okay. This hydrostatic equation when we have used, this is the density of the atmosphere, remember. On the other hand, you have the dynamic pressure of the solar wind, which is like this. Okay, fine. So now, what more we can do here is that ESW will be half. This is the number density, NSW, that is number of ions present per unit volume. Okay. This into MSW into the velocity, VSW square. Now, can we write this? Rho is equal to N into L? Yes, because this is number per unit volume and this is into mass. So, number of molecules or atoms or ions into mass will give you the total mass divided by the volume, which gives you the density, mass per unit volume. Okay, so just remember this is the number density, that is number of particles, charged particles per unit volume. Okay, just okay. Therefore, according to our equilibrium, that is half NSW MSW VSW square will be equal to E naught exponential of minus R minus R naught divided by H. This should be the equilibrium pressure of the atmosphere, which is equating with the dynamic pressure. So R minus R naught will be equal to H. Oh, sorry. If you do some calculations, so you will get it will be h, the scale height, log of 2p naught divided by nsw msw vsw square. So that is the final expression. So you can see this r will tell you about the ionopause, the height of the ionopause with respect to some height, that is some distance. Let's say r naught is the radius of the earth. So and from that distance, that is from the surface, at what height the ionopause will be there, based on the scale height, the P naught, and these values, if they are known, then we can calculate the height of the ionopause. Okay, so this is how the ionopause is calculated. Just a reminder, I have put it in the chat box. Uh, the meeting link, because this meeting will be going to expire in few minutes. Just copy that particular link or the code which I have given in the Google Meet. If it expires, then go to that and try to uh, write join that particular link. Okay, fine. So this is the height of the course. Fine. Next is yes. So when raised hand. Link नहीं दिख रहा? Oh, okay, just UDZ VEIN and QWB. VEIN QWB. Hmm. So let's start here. So, so we have now the intrinsic magnetosphere. We have talked about the ionophores, which is related to the induced magnetosphere. Now we will be talking about the intrinsic magnetosphere. So intrinsic magnetosphere, I have actually in detail have shown you that in the last session we have discussed about that. So what was that? That arc has its own magnetic field. That magnetic field interacts with the solar wind, and as a result, they form a magnetosphere, a magnetic, I would say, pool. Okay, so let me just therefore quickly write you. So I have shared one presentation where this magnetic field structure of the Earth is clearly mentioned. We have discussed in the last session, so that you can easily get. Okay, so in the documents or the lecture notes of these problem solving session, you will find that. Okay, so now here the geomagnetic field of many planets can be approximated by a dipole. Actually, it is a wrong statement. Geomagnetic field is only for the Earth. Geo represents only Earth. So better not to write geo, but the magnetic field. Okay, the magnetic field of many planets can be approximated by a dipolar structure. Okay, which is of the order of 1 upon R cube. Now, forcing by solar winds. This is a repetition, but still we are modify or modifies this field, creating a cavity called magnetosphere. Okay. Next is magnetosphere actually shelter from high energy solar winds. Okay, so the thing is very interesting that the magnetic field of the planet is interacting with the solar wind and creating a magnetosphere. And this magnetosphere in turn is protecting us from the solar wind. So a thing which is created between the interaction of the solar wind and the magnetic field of its own, creating a thing or a shape or a magnetosphere, and the same magnetosphere is now protecting us from the high energetic solar wind. So it is very important. Just like ionophore in the induced magnetism or magnetosphere, in case of intrinsic magnetosphere, we talk about a region of magnetopause. Okay, magnetopause. This is what we will be talking about when we are talking about the intrinsic magnetic field or magnetic field. So, what is magnetopause? It is when the Earth magnetic field pressure balances the solar wind pressure. See, the solar wind pressure will be similar to that of the dynamic pressure. Okay, so this is the equilibrium of this, that is P of the Earth magnetic field will be equal to P of the solar wind. This is what we will try to see. Okay, so any magnetic field or PB, I better to write. So PB is always B square upon 2 mu naught, whether it is for the sun, whether it is for the earth. But the field structure will change. For the sun, it is somewhat something. For earth, it is something. Okay. So let's say that BE is the field at Earth's equator. Okay. So what happens is that we can write this as R is equal BE square divided by mu naught N M VSW square. This is through the balance of this we can get. Okay. So what we assume here is that the B is actually E upon R cube, dipole structure. So if you put it, you will get BE square divided by 2 mu naught R cube, R to the power 6. Sorry. So this should be 1 by 6. Okay. And PSW you know from the previous expression, which is this one. Just put it here and you will get this part. Okay. So this R will represent the height of the magnetopause. Magnetopause. Okay. So these are the couple of things which are discussed. Okay. So this is fine, I guess. Anyway, if you have to calculate, you can just let me write it down one step I have skipped. So it is half, what was it? Rho SW. Oh, rho SW can be written as, just let me write. NW, sorry, SW, the number density, MSW, the mass, and VSW square. This should be equal to BE square divided by 2 mu naught and R to the power 6. Right. So R to the power 6 can be taken on the other side, and here you will have B square divided by 2 mu naught half NSW, MSW, VSW square. These two cancels, and you will surely get two. Just take the 1 by 6 and you will. Okay. So this is how the height of the magnetopause is calculated. So what we have seen is that there are the interaction of the solar winds can happen in two ways, and creation and that can result into two types of magnetosphere creation. Number one is the induced magnetosphere, another is the intrinsic magnetosphere. Okay, so the induced magnetosphere, in that case, we have seen that we have got ionopause. On the other hand, in case of intrinsic magnetosphere, we have the magnetopause. One case ionopause, another case magnetopause. Right? So these are the couple of things. Okay. Now we will talk about the acceleration of the solar wind. Okay. We will talk about now the acceleration of the solar wind. Okay. Just give me a moment. So in case of the acceleration of the solar wind, there are two models. One is, which we will start, that is the static model of corona. This is the first thing, the first attempt towards understanding the acceleration of the solar wind. Okay. And we will see that finally that this will lead to the whatever expression we will get. Through that, we will deduce that it is not really going to tell us about the acceleration because it will show some higher pressure. Okay, and you cannot use that to understand the acceleration of the solar wind. Rather, you have another theory which will be the Parker theory. So that is much more good theory compared to the static model of the corona. So let us try to finish at least the static model. Parker's theory maybe we can discuss in the next session, and if the time permits, we can go up to somewhat level. Okay, so first is the static model of corona. Okay, so first important thing which we will do is that we will use hydrostatic approximation. Okay, we'll use the hydrostatic approximation that is dpdr. See, this is for the corona. So remember, this is near the sun. So dpdr will be equal to minus rho into g, where rho now is the density of the plasma, not the Earth's atmosphere. Okay, this is near the sun now. So it's the density of the plasma. Okay, now rho can be written as n into m. We have seen that. Okay, where n is the number density. Let me write it again. Number density, number per unit volume. M is the mass of the plasma, which is or the volume which is there. In that, how much mass is present. Now, it can be written as n into me plus mi. That is mass of electron plus mass of ion. Of course, mass of ions will be much greater than the mass of electrons. So can be therefore written as n times m of I. On the other hand, we have pressure. According to the ideal gas equation, pressure can be written as n kBT divided by the V. So PV is equal to nRT, comes out to be P is equal to n kBT by V. So this gives you, oh, I'm sorry, this is, I think this will be capital N. The total number, this is now not the number density. Or you can just quickly write it as n kBT. That's all. So this gives you Ne plus Ni, separating the electron number densities and ionic number densities. Kb Boltzmann constant into temperature. So Ne, which will be always similar to Ni, which is equal to N. Can we write this assumption? Yes. Why? Because the number of ions will be almost equal to the number of electrons, because finally you have a plasma where charge where you have certain atoms or molecules, whatever are present. Because of the friction or heat or some energy, the atom or the molecule separated into ions and electrons, free electrons. So those ions and free electrons will be almost in a particular volume, will be almost having an equal number. This is one of the approximation, but it is a fine approximation. Okay. Therefore, then P, how can it be written? Can I write it as 2n kBT? Because you have a E and an I. So it will be 2n kBT. On the other hand, rho v, which we already have, is n into mi now, right? Why n into mi? Because only the total number density and the mass of the ions. We have already seen this. Okay. Therefore, can I write E is equal to 2 rho by mi kBT? Yes, we can. Just like this, n can be written as rho upon mi. We have just put this in this. Instead of n, we have put rho upon mi. So this gives you a particular equation. Let's say, okay, fine, leave it. Now, again coming back to this hydrostatic equation. So dpdr will be equal to minus rho times g, can be written as further dpdr is equal to 2 kbt divided by mi delta rho by delta r, okay, which is equal to minus rho g. So what we have done, we have just written dpdr as the ddr of this. Okay. So ddr of this will be, rho will be a function of r, only other things are constants, so can be taken outside. So 2 came outside, kb, t and mi, this came outside here, and delta rho delta, which will be equal to minus rho g. The next step is very clear. So delta rho by rho on one side, and you have g mi divided by 2 kbt and delta r on the other side. Starting from 0 to some r, that is base of the corona to some distance r. Okay, just from the photosphere, you can take this r equal to 0 as the photosphere, that is the surface of the earth, or the base of the corona, whatever you wanted to say, and r is some distance, some arbitrary distance. Similarly, rho at the base is rho naught, and at some r it is rho. So simply, this will be, the integration will be log of rho from rho naught to rho, and this gives you minus, oh, there will be a negative sign, sorry, minus mi g divided by 2 kbt, and it will be just r. All right. So you finally get your expression as rho is equal to rho naught exponential minus mig divided by 2 kbt into r. Okay, so this is your final expression of the density. So what we can see from here, what we can deduce from here is that density decreases exponentially as we move away from the surface. Okay, so density of what will become the plasma or the solar wind. All right. Now comes couple of important things. For example, comes the thermal conductivity. There are couple of expressions as you will see. Conductivity, okay, which depends on the electron conductivity, because in plasma mostly ions and electrons are present. So thermal conductivity will be majorly contributed by the electron conductivity. So that is about 0.324, 32% of the electric conductivity. This is the total thermal conductivity. And then you have corona charge flux. So these are now completely coming into the solar terms. So Q will be equal to minus K grad T. This is what the expression happens. And K is equal to, let's say, K naught T to the power 5 by T. The thermal conductivity is depending on temperature to the power 5 by 2. And del dot Q is equal to 0. So this is possible in the absence of source and sink. You can understand this based on your mass continuity. What we say, in the absence of any source or sink of mass, the density times velocity is equal to 0. This is what we like. And this is what we call as the mass flux. Right. Here it is the coronal charge flux, Q. Okay. Which is defined like this, and K is Q. Okay. So del dot q equal to 0. Remember, this is the charge flux, not the charge. Okay. In the absence of source and sink, del dot q can be equal to 0. Similar thing, just in case of the coronal mass flux, this is how the q is defined. So now del dot q has its own expression. What is that? K naught t to the power 5 by 2 and grad t. This is equal to 0 based on this in the absence of source or sink. Okay. So this is now what we will do is that we will assume we will assume spherical symmetry. Okay. So spherical symmetry means that in all directions, particularly the radial direction, things are similar. Okay. The amount of the fluxes, the charge fluxes will always be similar. And by that, what we mean is that radial, only the radial direction has to be considered. So only the radial direction is to be considered. All right. So now, if you have to write the divergence and the gradient in terms of what you call as the spherical symmetry or radial direction, you will get something like this: 1 by r square ddr. Since we are taking only radial symmetry, we will not write partial derivative. We will write the total derivative. Okay, r square k naught t to the power 5 by 2. Now grad t can be written as dt dr. This is equal to 0. 1 by r square. So divergence. So del dot something from a. Okay. Only if radial component has to be taken, it will be 1 by r square del r square something that a. Okay. Just remember that. But since we are taking only the radial direction, so it will be ddr. Similarly, in case of gradient, dt by dr. Simple. Okay. But the total derivative has to be taken. That's the important point. Fine. Let's do further. So if 1 by r square ddr of this is equal to 0, can we write r square k naught t to the power 5 by 2 dt by dr is equal to constant, right? We can write because derivative of some quantity is equal to 0. So we can put that quantity as constant. All right. Next, you can understand. Now we will just integrate it. T to the power 5 by 2 dt is equal to some constant c, let us say r. So c by r square k naught dr. Now we will be integrating. Okay. So this will give you 2 by 7 t to the power 7 by 2. And this will give you c by k naught, which are the constants, and 1 by r with a minus 7. Okay. Now putting the limits. So r is equal to r naught. Again, you can choose this as the surface of the sun or the base of the corona, which is equal to t is equal to t. And as r tends to infinity, that is, generally we talk about interstellar space. Interstellar space means you, let's say, from the sun, you escape the solar system and goes to some more distance beyond the solar system. Okay, so that is the interstellar distance. T will be tending to 0, almost. This is the again assumption. It's a kind of a boundary condition. Okay, this is kind of a boundary condition. If T tends to 0, T is equal to 0 is not possible. So it is just an assumption. Just remember. Okay, fine. So let's go ahead. So 2 by 7 So what you get? T naught to the power 7 by 2, applying this limit, you get minus T by K naught into minus 1 by R naught. Oh, I do. Minus is already. So now what will you do? So minus T by K naught again into 7 by 2 will be equal to T to the power 7 by 2 into R. Using, you're not using this limit, it's just general expression. So now what you have is that R naught T naught to the power 7 by 2. So you, from here you can deduce that R into T to the power 7 by 2 is constant, right? So then, based on the limits, can we write like this? Yes, we can write this. Okay. So now, what we will do is that we will take T by T naught to the power 7 by 2 is equal to R naught by R. So T is equal to T naught R naught by R to the power 2 by 7. This is the expression of the temperature. So what you will get as R tends to infinity, T is tending to 0. The whatever limit we have got. Okay. Now one more step is required to understand to get the final expression of the pressure. Because from the pressure difference only the acceleration will uh, we will get the acceleration terms. So we will go towards the pressure and we will compare it with the real interstellar pressure observed. Okay, and then we will say that whether we can go ahead for acceleration or not. Okay, so this is one of the expressions just to remember because we will be using this. So coming back again to the hydrostatic. So what was that? DDR of 2 rho kb T divided by mi is equal to minus rho times G. Now, what we will do is that we will define the gravity of the sun is G m naught by r square. Where m naught is mass of the sun. So just like we define gravity for the earth, similarly for the sun. Also, we have the expression that is T is equal to T naught, how temperature varies with distance, 2 by 7. Now, these two, we will try to put it here. So, DDR now can be written as therefore 2 rho K divided by Mi. T, in place of T, we can write this R naught by R to the power 2 by 7. This is equal to minus rho Gm naught by R square. Okay, so remember rho depends on R. Rho is a function of R, so you cannot just really get away with it. Fine, the other terms can be taken outside. So 2 kb, mi, t naught, these are all constant. In fact, R naught to the power 2 by 7 can also be taken out. So what you left behind is this ddr of rho into 1 by R to the power 2 by 7. Okay, and you will have a, okay, so further you will have this gm naught can be taken here. Okay, and you get something like 1 by R square. All right, so this is what you get finally. And if you further solve it, you will get I'll just write the direct expression. I will not write much into the details. It will be rho naught r by r naught to the power 5 by 7 exponential 7 by 5 g m naught mi divided by 2 kb t naught r naught. Very complicated expression. And you have r naught by r to the power 5 by 7 minus 1. So what you get is that as r tends to infinity, what will happen? As r tends to infinity, your density also tends to infinity. Exponential, maybe this will be a negative constant quantity, but this will tend to infinity. But what about pressure? PR. If you look at the pressure, it will come out to be, its expression comes out to be exponential of 7 by 5 g m naught mi divided by 2k t naught r naught into r naught by r to the power 5 by 7 minus 1. Here what happens is that as r tends to infinity, so PR becomes some constant. Right? As r tends to infinity, this becomes 0, minus 1 will be there, and these are all constant. So PR is constant. Now, how much value from the static model of corona, the pressure we are getting as some at large distances? So practically at large distances, we get this as 10 to the power minus 5 Pascal. However, the actual observation that is at large distances from the sun, you get the interstellar pressure as 10 to the power minus 15. So you can see that static model of corona. So static model of corona shows larger pressure, or predicts, I would say, larger pressure compared to observation. So what happens is that why this theory is not good, because if you have a sun here, okay, and it has near the photosphere, suppose it has some pressure P1, the acceleration of the solar wind will happen based on the pressure gradient force. So this should be some P. So P should be much, much less than P1. Then only you will have a strong acceleration. Okay. But what happens here is that the pressure is not that small. Hence the acceleration will be not that huge. Okay. What we generally see. So hence, because of this, this is a failure. Okay. So static model of corona fails in getting the real interstellar pressure. Then comes the Parker's theory. So what I will do is that in the next 10 minutes, I will try to uh, give an idea of the Parker's theory of the solar wind acceleration, the basic things, and maybe write some basic equations. And in the next session, that is on Friday, this Friday there is a session 6 to 8 p.m. There we will complete the week 12 contents and finish the course contents. Now, the next session in the next week, that is on Tuesday, next Tuesday, we will solve some good amount of numericals so that it will be helpful for your exam. Okay, so that is the plan till now. Okay, so next is the Parker theory. So we will talk about this. The Parker's theory of solar wind acceleration. Okay. So this theory is discovered first in 1958 by E.N. Parker. Okay. So we will be talking about the general basic details of the Parker's theory, particularly its assumptions, what processes we are really talking about. Those things we will be talking about. Just give me a moment. Okay. First of all, in Parker's theory, there are a couple of things. So first of all, how does this solar wind escapes the sun's gravity? Because sun has a huge mass, the sun's gravity will be huge. So how does the solar wind escapes? So the process is, let us first jot down the couple of points before moving towards the long derivation. So processes that enable solar wind to escape the sun's gravity. Okay. So first of all, this has a supersonic velocity, which is, we have discussed this supersonic velocity, which is greater than 400 kilometer per second. So this is one of the important points. So this itself has a very huge velocity. But why? So what happens is that, first of all, because of strong heating, okay, plasma gets huge energy. Okay, this is one of the points. Next is, it also gets compressed first, and finally it gets expanded. Expansion. So what is happening is that, because in the sun you have high temperature and also you have high pressure. Okay, because of high temperature and high pressure, these two processes are happening. One is the plasma, which is present near the surface of the sun, gets huge amount of energy and gets compressed because of the pressure. But as you go away from the sun, okay, your pressure decreases rapidly. As the pressure decreases rapidly, the pressure gradient force becomes very, very strong. And because of this pressure gradient force, okay, the solar wind tend to accelerate. The solar wind accelerates, okay, because the acceleration is present based on the pressure gradient force. And this is termed as this sudden pressure drop or sudden pressure change is termed as the expansion process. Okay, so there is a high pressure region near the sun and there is a low pressure region, not a low pressure region, but surrounding the sun. As you go far away from the sun, there are regions of the lower pressure. This creates a pressure gradient force and resulting into the highly heated and compressed plasma to expand. And that expansion results into solar wind to accelerate. Okay, so this is the main fundamentals of this solar wind acceleration. Okay, and this is how the solar wind escapes. So, couple of phenomena are important. So, escape of plasma from the sun's gravity. There are many processes. Gravity uh, happens due to number one is high temperature. Number two, some magnetic phenomena are there. Okay. Third is electric phenomena are there, but these are very little compared to the pressure differences. And combined together, you have some electromagnetic phenomena. So major thing is this the high temperature plus the high pressure which is present near the sun. That and the drop in the pressure creating a pressure gradient force. Okay, so this is what how the plasma gets away or from the sun's gravity. Okay. Now, before going into the deep derivation, we must list some of the assumptions which are used in the Parker's theory. So, assumption. I'm not actually in fond of starting the derivation right now because it is a huge derivation. It will take some time. So, better to uh, do it on the next session. And we will discuss about some space weather and all those things. Okay. So, let us first list down the assumptions. So, first one is that solar wind can be treated as an ideal gas. Okay. Number two, the flow is radially away from the sun. We are not taking any other components. Okay. So it is only radially away from the sun. That is spherical symmetric assumption. Third is acceleration due to EM fields, electromagnetic fields, are small and hence can be reduced. You will see that we will write an expression and then we will neglect that. And the fourth is the solution is time stationary, not changing with time. So the solution will not be a function of time. Okay. And what processes we will be used, the physical physics what we will be using is the conservation of mass, momentum, and heat. These are the three physical processes which we will be using. So actually this process is or this Parker's theory based on some a term called magnetohydrodynamics. It's a huge term. Okay. And here some more assumptions are there, like the plasma is assumed to be a single fluid. Okay. This is let's say 60, no difference between electrons and atoms. This is the sixth. And this is not an assumption, but just a thing to write. Frequent collisions and strong external magnetic field can create large number of electrons or ions. Okay, these are couple of assumptions. So the first thing which we will be using is the mass continuity, that is delta rho delta T plus del dot rho u. Very familiar expression. We have seen this earlier also when we were talking about the mass conservation in the lower atmosphere. So this is the first equation which we will be using. And then you will have the momentum equation. We will start it from here only in the next session. Delta u by delta T plus u dot grad u. You can see the nonlinear terms of the momentum equation is minus gradient of P, the pressure gradient force, which is very important, plus J cross B. So this is something related to the electric. This is something related to the magnetic. Okay, and plus rho times the gravity of G. Okay, and what is J? The current density actually is sigma times E plus U cross B. Okay, this is the current density. I'm sorry, this is not the. Yeah, this is the current. Okay, so these are the couple of equations which we will be using, out of which we will remove this, the electromagnetic term, J cross B. This we will remove later on, and using the spherical symmetry, that is radially going in all directions, we will try to solve for it. And you will find that again we will make a wrong choice, and that will create a problem. And then we will go towards the right way or the right direction. Okay, so it's a long derivation, so we will be continuing in the next session and try to figure out that what exactly this Parker's theory of solar wind acceleration leads to finally. Okay, and then if that day time permits, we can discuss about the space talk, because we have, yeah. Uh, okay. Question is that what will be the format of the exam? I think MCQ. Advanced atmospheric physics will be completely MCQ questions, because in the assignment also you have seen that. But one thing I will tell you to do is that you ask the NPTEL discussion forum that whether there will be an essay type question present or not. Okay, just ask it in the NPTEL forum, because I haven't given any exam of this advanced atmospheric physics, but just to confirm, just put it in the NPTEL discussion forum. One of the NPTEL people will guide you. Okay. And one question, one thing I have got in mail about the scientific calculator. Just uh, click the link and try to see how to use the scientific calculator, because you will not be allowed the actual calculator. So practice it. If you have a numerical, let's say if you join next Tuesday, our problem solving session, we will be doing numericals. Practice it through that calculator and see how much time it takes. So that will be helpful for you. Okay. So these are the couple of things. Okay. So we will talk about the Parker's theory in the next session, which is on Friday. You will get a mail. Okay. Friday, 6 to 8 p.m. Okay. So let's then leave it for today then. Okay. Thank you. Or if you have any other question, you can